Welcome to the Introduction to Low-Level Design or LLD. In this session, we will explore the core concepts of LLD, its importance, and how it fits into the software development lifecycle. Today's session will cover an introduction to LLD, its difference from high-level design, and the key concepts that make up LLD. We will also look at practical examples to reinforce the concepts. Low-level design or LLD refers to the detailed design of your system components. It describes how each component will be implemented, focusing on the individual parts of the system rather than the entire architecture. LLD serves as a bridge between high-level system architecture and the actual code implementation. It includes the design of components like classes, methods, algorithms, and data structures. High-level design or HLD focuses on the overall system architecture. It outlines what needs to be done but does not detail how it will be done. It is abstract and module level. On the other hand, LLD delves into the specifics of implementation. It focuses on individual components like class definition and method behaviors. The audience for HLD typically includes architects and stakeholders, while LLD is meant for developers. In LLD, the most fundamental concepts are classes and objects. A class is a blueprint for objects, which are individual instances of that class. For example, a car class could have car object like sedan or SUV. LLD also involves attributes and methods. Attributes are the data members such as the car's color or speed. Methods represent actions that can be performed like accelerate or brake. Another important concept is the relationship between classes. These relationships include association, aggregation, composition, and inheritance. For instance, a car might be associated with a driver. Abstraction and encapsulation are also critical in LLD. Abstraction hides the complexity, showing only the necessary details, while encapsulation controls how data is accessed and modified through methods. LLD emphasizes scalability and maintainability. The goal is to design a system that is modular and easy to extend or modify over time. LLD is essential because it ensures a thorough understanding of how the system will be implemented. By designing the system in detail, potential issues can be identified before coding begins. LLD also fosters better collaboration between team members. That design documentation acts as a shared reference for all involved in the project, promoting smoother integration and fewer errors. Let's now apply this concept with an interactive example. We will design a library management system which involves several entities like books, members, and librarians. Here we will define classes for each entities. A book class might have attributes like title and author, while a member class might have methods like borrow book and return book. Now it's time for a quick Q&A session. Feel free to ask any questions you might have about the concepts we have covered so far, or share your thoughts on applying LLD in real-world projects. For your hands-on assignment, define the class diagrams for a food delivery system. The system should include classes such as restaurant, order, customer, and delivery person. Think about a relationship between these classes. To recap, low-level design is a critical part of software development. It ensures that systems are maintainable and scalable, and it clarifies the specific details of how each component should work. Remember, LLD helps bridge the gap between high-level design and actual implementation. It focuses on the fine details like classes, attributes, methods, and relationships, ensuring the system can be easily maintained and extended. Thank you for attending today's session on low-level design. We hope you have a deeper understanding of LLD's importance and how to apply it. If you have any further questions, feel free to reach out. Welcome to the session on Object-Oriented Design or OOD. In today's lesson, we will dive into the fundamentals of object-oriented design, its key concepts, and how they form the backbone of modern software development. Let's get started. First, let us understand what object-oriented design or OOD is. OOD is a design methodology based on the concept of objects, which can hold data in the form of attributes and behaviors in the form of methods. The core principle of OOD is to organize software design around these objects, making systems modular and easier to understand. Why do we use OOD? The primary reasons are to promote reusability, maintainability, and scalability. It ensures modular development, meaning that each object can be worked on independently, enhancing the flexibility of our system. Furthermore, encapsulation allows developers to manage complexity effectively. Let's now explore classes and objects, the foundation of OOD. A class is a blueprint for creating objects. It defines the properties or attributes and the behaviors or methods that the object will have. Objects, on the other hand, are instances of a class that hold actual values for those attributes. To give an example, consider a class named car. It may have attributes like brand, model, and year. You can create different objects of the car class, such as car1, car2, each with specific values for those attributes. Here's a simple code example to represent this. Moving on to inheritance, which allows one class to inherit the properties and behavior of another. Inheritance enables code reuse and allows us to create a hierarchy of classes. A parent class defines common behaviors and child classes can extend or modify these behaviors. Here we have an example where we have a base class vehicle with a method start engine. We then define a car class that inherits from vehicle and adds its own method drive. This demonstrates the power of inheritance, as car can use the start engine method from vehicle while adding its own functionality. Now let's talk about polymorphism. Polymorphism allows us to treat objects of different classes in a uniform way. There are two main types of polymorphism: compile-time polymorphism or overloading, and runtime polymorphism or method overriding. Let's focus on method overriding. In our example, we have an animal class with a method sound and a derived class dog that overrides this method to provide its own implementation. This demonstrates how polymorphism allows different behaviors for the same method depending on the object that invokes it. Encapsulation is the practice of bundling data and methods that operate on that data into a single unit or class while restricting access to some components. This helps protect the integrity of the data by controlling how it can be accessed or modified. For example, we can define a class employee with private attributes name and salary. Public methods set salary, and get salary allow controlled access to these attributes, ensuring that data remains consistent and secure. Next, we have abstraction. Abstraction focuses on hiding the implementation details and exposing only the relevant functionality. This simplifies interaction with complex systems by providing a high-level interface while hiding the complexities behind the scenes. In this example, we have an abstract class shape with a pure virtual method draw. The class, the circle class derives from shape and implements the draw method. Abstraction allows us to work with different shapes without worrying about their specific implementations. To summarize, we have covered the key concepts of OOD, starting with classes and objects. Classes define the structure and behaviors of objects, while objects are the instances that hold actual data. Together, they form the building blocks of object-oriented design. We also explored inheritance, which allows us to reuse code and create class hierarchies, and polymorphism, which allows one interface to represent multiple behaviors. These principles are essential for creating flexible and extensible systems. Encapsulation ensures data integrity by restricting access to certain parts of an object, while abstraction simplifies complex systems by hiding implementation details. Together, these principles help developers create robust and maintainable systems. Now it's time to put what we have learned into practice. For our first exercise, create a bank account class with methods to deposit, withdraw, and check the balance. This will give us hands-on experience with object-oriented principles like encapsulation and methods. For the second exercise, design a class hierarchy for vehicles such as car, truck, and bike. Each of these classes should share common behaviors, but each type should also have unique methods. This will give us practice with inheritance and polymorphism. In the final exercise, implement a polymorphic solution for a shape class hierarchy. Create classes for circle, square, and triangle, each with a draw method. Use polymorphism to draw the shapes in a consistent manner. To conclude, object-oriented design is a powerful methodology for creating scalable and maintainable software systems. By mastering key components such as classes, objects, inheritance, polymorphism, encapsulation, and abstraction, we can design robust systems that are both efficient and easy to maintain. Thank you for your attention and happy coding. Welcome to this presentation on Solid Principles, Part 1. Today we will be diving into the single responsibility principle and the open-closed principle. Let's get started. First, let's talk about what Solid is. Solid is a set of 5 design principles used in object-oriented programming. These principles help developers write clean, maintainable, and scalable software. By following Solid, developers can ensure that the software is flexible and easy to adopt over time. Here's a breakdown of the SOLID acronym. S stands for Single Responsibility Principle. O stands for Open Closed Principle. L stands for List Scope Substitution Principle. I stands for Interface Segregation Principle. D stands for Dependency Inversion Principle. In this session, we will cover the first two principles, Single Responsibility Principle and Open Closed Principle. Let's start with the Single Responsibility Principle or SRP. This principle states that a class should have only one reason to change. In simpler terms, each class should be responsible for only one job or functionality. Why is SRP important? By adhering to this principle, we can make our code more readable and easier to maintain. When a class has only one responsibility, it is easier to test, debug, and extend. SRP also encourages modular design and reduces the risk of bugs when changes are made. Let's look at an example where SRP is violated. Suppose we have a report generator class. This class is responsible for three things: generating a report, saving the report to a file, sending the report via email. In this case, the class has multiple responsibilities. If we need to change one of these, we risk affecting the others, making the code harder to maintain. To follow SRP, we can break the report generator class into three separate classes, each with a single responsibility. Report, responsible for generating the report; file manager, responsible for saving the report to a file; email service, responsible for sending the report via email. By doing this, we ensure that each class is responsible for just one task, making the system more flexible and maintainable. Next, let's discuss the open-closed principle, or OCP. OCP states that a class should be open for extension but closed for modification. This means that we should be able to add new functionalities to a class without changing its existing code. Why is OCP important? By following OCP, we can extend the behavior of a class without modifying the existing code. This reduces the risk of introducing bugs in the existing functionality and makes the code base more stable and scalable. Let's look at an example where OCP is violated. Suppose we have a graphic editor class that handles drawing different shapes like circles and rectangles. Each time we add a new shape, we modify the graphic editor class. This makes the class difficult to extend and increases the chances of introducing bugs. To follow OCP, we can use inheritance and interfaces. We can create a shape interface with a method like draw and have each shape class like circle and rectangle implement this interface. The graphic editor class will then handle all shapes uniformly, and adding new shapes will not require modifying its code. To recap, the single responsibility principle ensures that a class has only one reason to change, which leads to more maintainable and testable code. The open-closed principle tells us that a class should be open for extension but closed for modification, allowing us to add new functionality without changing existing code. Both principles help in creating flexible and clean software. Let's put our learning to practice. For the first exercise, refactor the following order processor class to follow the single responsibility principle. Right now it handles multiple responsibilities. How would you separate them into individual classes? For the second exercise, refactor the zoo class to follow the open-closed principle. Right now the class checks for different animal types and modifies its behavior based on them. How can we change the design so that adding new elements won't require modifying the zoo class? To conclude, today we learned about the single responsibility principle and the open-closed principle. These principles are the foundation for writing clean, maintainable code. Next time we will be discussing the list scope substitution principle and the interface segregation principle. We encourage you to explore these concepts further and think about how they apply to your own project. Welcome to today's session on solid principles. In this part, we will focus on two important principles, the Liskov substitution principle and the interface segregation principle. Let's dive into these concepts and see how they impact object-oriented design. Today's session will cover an overview of the two principles, Liskov substitution and interface segregation. We will explore the definitions, key points, examples, and code demonstrations to help solidify our understanding. The Liskov substitution principle or LSP is a core concept in object-oriented design. It states that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. Let's explore what this means in practice. LSP ensures that derived classes extend the functionality of the base class without altering its behavior. It promotes the safe use of inheritance in object-oriented design. Violating this principle can lead to unexpected behavior and bugs in our code. Key points to remember about LSP. First, derived classes should not change the behavior of the base class. Second, LSP allows for the safe extension of functionality. Finally, violating LSP can result in bugs, which is why it's essential to follow this principle. Let's look at an example where LSP is violated. Consider a rectangle class with a square subclass. The issue here is that square alters the inherited behavior of the rectangle class, which leads to unexpected behavior. Here's the code that demonstrates the violation. The square class inherits from rectangle but changes the behavior of the setWidth method, which results in incorrect behavior when the object is used in the same way as a rectangle. The correct approach is to avoid inheriting from rectangle altogether. Instead, separate the rectangle and square into distinct classes, each with its own specific behavior. Here is the corrected code. By making rectangle and square separate classes, we ensure that we don't violate the Liskov substitution principle and avoid altering inherited behavior. Moving on to the integration segregation principle or ISP. ISP states that clients should not be forced to depend on interfaces they do not use. This principle promotes the use of smaller, more specific interfaces rather than larger general ones. To follow ISP, create multiple small interfaces instead of a large one. This avoids unnecessary dependencies and ensures that clients only depend on the methods they need. Key points to remember about ISP. First, clients should not be burdened with unnecessary methods. Second, small role-specific interfaces are preferred over large generalized ones. Finally, ISP improves code modularity and reduces unnecessary dependencies. Now let's look at an example of an ISP violation. Consider a large printer interface that forces all classes implementing it to implement unnecessary methods like scan and fax, even if they only need to print. This code demonstrates the violation. The printer interface forces a class to implement methods it may not need, leading to unnecessary dependencies. This violates the interface segregation principle. To fix this, we can split the printer interface into smaller, more specific interfaces. For example, create separate printable, scannable, and faxable interfaces, each defining a single method. Here's how we can apply the correct approach to ISP. By separating the interfaces, we ensure that clients depend only on the methods they need, reducing unnecessary dependencies. For a practical exercise on LSP, we will create a shape class with a getArea method that can be extended by a circle and class triangle classes. The goal is to ensure that substituting a base class object with a derived class object does not cause any issues. For ISP, let's design a system where we split the machine interface into smaller, more specific interfaces like coffee maker, juice maker, and tea maker. This way, classes can implement only the interfaces they actually need. Let's recap the key benefits of LSP. The scope substitution principle ensures that derived classes can safely substitute base classes objects without breaking functionality. This promotes stable and predictable behavior in object-oriented systems. Similarly, the interface segregation principle reduces unnecessary dependencies, improves modularity, and ensures that classes only implement the methods they actually need. Both principles lead to cleaner, more maintainable code. To wrap up, remember that LSP allows safe substitution of base class objects, while ISP encourages smaller, more specific interfaces. Both principles play a crucial role in creating robust and maintainable software. Thank you for your attention. Now, let's open the floor for any questions or discussions. Feel free to ask about any concepts or examples we have covered today. Welcome to the presentation on the dependency inversion principle, part 3 of the solid principles of object-oriented design. In this presentation, we will explore the concepts and importance of dependency inversion, how to implement it, and its real-world applications. The dependency inversion principle, or DIP, is a fundamental design principle that suggests high-level modules should not depend on low-level modules. Both should instead depend on abstractions. This allows us to decouple different parts of the system, enhancing flexibility and maintainability. DIP goes further by stating that abstraction should not depend on details. Instead, details should depend on abstractions. This helps in creating more flexible systems where the core logic does not rely on the specifics of lower level implementations. Let's look at why DIP is so important. First, it enables decoupling between components. When high-level modules don't rely on low-level ones, changes in one module won't require changes in the other. This leads to better system modularity. DIP also increases testability by making it easier to mock dependencies in unit tests. Furthermore, it makes the system more extensible. When new functionality is needed, it can be added without changing existing code, keeping the system adaptable. Common violations of DIP include directly instantiating classes instead of using abstractions, and having high-level modules depend on low-level modules. Concrete implementations. These issues create tight coupling, making it harder to change and make the system over time. So, how do we implement DIP? One approach is to use interfaces or abstract classes. This allows us to define contracts that high-level modules can depend on rather than concrete classes. Additionally, dependency injection is key in implementing DIP effectively. Another essential practice is inversion of control or IOC. IOC frameworks manage the instantiation and injection of dependencies, allowing us to focus on business logic while keeping our code decoupled and maintainable. Here's an example of using interfaces in C++. We define an interface iNotification service with a method for sending notifications. Notice that high-level modules will depend on this interface, not on any specific implementation such as email notification. As we implement the email notification class, it adheres to the iNotification service interface. This ensures that high-level modules can interact with any notification method without needing to know the specifics, following DIP's principles of abstraction. Dependency injection (DI) is one way to implement DIP. DI involves passing dependencies into a class rather than having the class create them itself. The two common types of DI are constructor injection and setter injection, both of which help decouple components. Another type of dependency injection is interface injection, where the dependency provides an interface to allow the client to inject its dependencies. This further strengthens the decoupling between classes and makes the system more flexible. Here's a practical example of constructor injection. In this case, the application class receives a logger dependency via its constructor, ensuring that the high-level module does not directly instantiate a logger. This implementation allows flexibility and easy testing. Inversion of control is a key part of implementing DIP. IOC allows external frameworks or containers to manage the lifecycle of dependencies. This means that instead of your code managing dependencies, an IOC container handles this responsibility. Some popular examples of IOC frameworks include Spring for Java, Unity for C Sharp, and Boost.di for C++. These frameworks manage the creation and injection of dependencies, ensuring that the code remains decoupled and flexible. DIP brings several advantages to a system. First, it improves reusability. Since high-level modules rely on abstractions, the underlying details can be changed without affecting the rest of the system. This leads to more reusable code. Another benefit is flexibility. With DIP, it's easy to replace components with the new implementations, allowing us to adapt to changes quickly. Unit testing is also made easier as we can mock dependencies rather than having to deal with complex real implementations. Let's look at a real world example. Imagine a payment system where the payment processor class depends on different payment gateways. Using DIP, the payment processor depends on an abstract iPayment gateway interface, allowing for multiple implementations without altering the core logic. As shown in this example, the payment processor class interacts with the IP gateway interface, not specific implementations. This ensures that new gateways can be added without changing the payment processor logic, adhering to the principles of DIP. In conclusion, the dependency inversion principle is essential for creating flexible, maintainable, and decoupled systems. By relying on abstractions and using techniques like dependency injection and inversion of control, we can build scalable applications that are easier to test and modify over time. Welcome to the presentation on design patterns. Today we will dive into key concepts, explore different types of design patterns, and look at practical examples to help us understand how these patterns can improve software design. Design patterns are reusable solutions to common design problems faced in software development. They provide standardized approaches for solving recurring issues. By applying these patterns, developers can improve code quality, scalability, and maintainability, ultimately making the development process more efficient. Using design patterns brings several benefits to developers. First, they improve code quality by reducing redundancy and encouraging best practices. Second, they speed up development as developers can leverage proven solutions instead of reinventing the wheel. Third, they make the code easier to maintain by promoting modularity. And finally, design patterns provide a shared vocabulary, making collaboration between team members easier. Design patterns can be categorized into three main types: creational, structural, and behavioral. Creational patterns deals with the process of object creation. Structural patterns focus on the organization of classes and objects, and behavioral patterns manage the interaction between objects. To elaborate further, creational patterns like singleton and factory method helping in managing object creation. Structural patterns such as adapter and bridge deal with the composition and relationships between objects. Lastly, behavioral patterns like strategy and observer handle object interactions and communication. Creational patterns focus on object creation. The singleton pattern ensures that a class has only one instance and provides a global point of access. The factory method defines an interface for creating objects, but it allows subclasses to decide which class to instantiate. Other creational patterns include the abstract factory, which provides an interface for creating families of related or dependent objects, and the builder pattern, which constructs complex objects step by step. The prototype pattern creates new objects by copying existing ones, saving time and resources. Structural patterns help to compose classes or objects to form larger structures. The adapter pattern converts one interface into another, while the bridge pattern separates abstraction from implementation, allowing for independent variation. The composite pattern combines objects into tree-like structures, treating both individual objects and compositions uniformly. The decorator pattern adds behavior to objects dynamically without altering their structure. The facade pattern provides a simplified interface to a complex subsystem, and the flyweight pattern reduces memory usage by sharing objects. Finally, the proxy pattern provides a surrogate or surrogate or placeholder for another object. Behavioral patterns deals with the communication and interaction between objects. The chain of responsibility pattern passes requests along a chain of handlers. The command pattern encapsulates a request as an object, allowing for parameterization of clients. The interpreter pattern defines a grammar for interpreting sentences, while the iterator pattern provides sequential access to elements in a collection. The mediator pattern reduces communication complexity between objects, while the momento pattern captures and restores an object state. The observer pattern notifies all observers when an object's state changes. The state pattern allows an object to alter its behavior when its internal state changes, and the strategy pattern defines a family of algorithms, making them interchangeable. The template method pattern defines the skeleton of an algorithm, and the visitor pattern adds operations to objects without modifying their classes. Learning design patterns is important for several reasons. They allow us to solve real world problems more effectively, and they are often a crucial topic in software engineering interviews. Additionally, many popular frameworks like Spring and Django rely heavily on design patterns, making them essential in real world applications. Let's look at a practical example of the singleton pattern. This pattern ensures a class has only one instance and provides a global access point to that instance. A common use case for singleton is in managing shared resources like a logger or a database connection. Next, let's explore the factory pattern. This pattern provides an interface for creating objects without specifying the exact class of the object. For instance, a shape factory might create different types of shapes, such as circles or squares, based on user input, abstracting away the details of object creation. To learn design patterns effectively, start by understanding the problems each pattern solves. Once you grasp the problem, move on to learning the structure of each pattern. It's essential to understand how they work before applying them in your own code. Next, practice implementing the patterns in different scenarios. Try to apply them to real world problems. Analyze how design patterns are used in popular frameworks like Spring, Django, or React to gain further insights into their practical use. Now, let's move on to some interactive exercises. First, implement a singleton pattern for a logger class. Then create a factory pattern for drawing different shapes like circles and squares. Finally, discuss real-world examples of patterns such as the observer pattern in a web browser. In conclusion, design patterns are essential tools for creating efficient and scalable software systems. By understanding and applying these patterns, we will be able to solve design problems more efficiently, write more maintainable code, and improve our collaboration with other developers. Keep practicing, and soon you will see the benefits of using design patterns in your daily work. Welcome to today's presentation on a recap and practical examples, applying design principles and patterns in code. In this session, we will be revisiting low-level design and object-oriented design principles, and we will dive into practical coding examples. Let's get started. Here's the agenda for today's session. First, we will recap key concepts of low-level design and object-oriented design. Then we will move into practical coding examples to solidify our understanding. Lastly, we will explore real-world use cases and have a discussion on how to apply these principles effectively. Let's start by revisiting low-level design. LLD is about translating the system's high-level design into detail implementable solutions. It focuses on class designs, methods, data structures, and their interactions. The key difference between low-level design and high-level design is that HLD covers system architecture and module interactions. LLD deals with the finer details of how each component is built and interacts with others. Now let's recap object-oriented design. The core concepts of OOD include classes and objects, encapsulation, abstraction, inheritance, and polymorphism. These concepts help us build flexible and reusable systems. Classes define the blueprint, while objects are instances of those classes. Encapsulation ensures that the data is hidden within objects, while inheritance and polymorphism provide mechanisms for reusability and dynamic behavior. Next, we will quickly recap the first two solid principles. The single responsibility principle (SRP) states that each class should have only one reason to change, which simplifies maintenance. The open-close principle tells us that classes should be open for extension but closed for modification, allowing us to add new features without altering existing code. Let's move on to the next two solid principles. The Liskov substitution principle says that objects of a superclass should be replaceable with objects of a subclass without affecting functionality. The interface aggregation principle (ISP) suggests that clients should not be forced to implement interfaces they do not use, promoting cleaner and more manageable code. Finally, we have the dependency inversion principle (DIP). This principle encourages decoupling high-level modules from low-level modules. Both should depend on abstractions, which allows for more flexible, testable, and maintainable code. Design patterns are reusable solutions to common software design problems. There are three main types of design patterns: creational, structural, and behavioral. Creational patterns deal with object creation. Structural patterns focus on organizing components, and behavioral patterns handle object interactions. Let's look at a practical example of the single responsibility principle. Imagine we have a class that handles both user authentication and login. Following SRP, we separate the concerns into two classes: authentication service for authentication and logging service for logging. This makes the system easier to maintain and extend. Next, we will apply the open-closed principle using the strategy pattern. Suppose we need to support multiple payment methods in an e-commerce application. Instead of modifying existing classes, we extend the functionality by introducing new strategy classes for each payment method. This way, our system can easily accommodate new payment methods without altering existing code. Now, let's see the dependency inversion principle in action. We have a notification system, and instead of tightly coupling high-level modules like notification service to low-level modules like email service, we use dependency injection. This way, we can easily swap out the email service with another service, promoting flexibility and decoupling. Let's consider a real-world example of a library management system. By applying solid principles, we can design a scalable and maintainable system. For instance, by using the open-close principle, we can add new features like book reservations or fines calculation without changing the core logic of the system. Here's another example: an e-commerce checkout system. Applying solid principles in this case, ensures that the system can easily handle multiple payment options, discounts, and user promotions without cluttering the code. It also helps in maintaining clean separation between modules like card management, payment processing, and order fulfillment. To summarize, we have gone through key design principles and patterns, including solid principles and their application in real world examples. Now, I would like to open the floor for any questions you might have. Feel free to ask for clarifications on anything we have covered. Thank you for attending today's session. I hope you found the content useful. If you have any further questions or would like to continue the discussion, feel free to reach out to me. I look forward to seeing you in our next session. Have a great day.